still I didn't give precise statement of the theorem, but in the proof, what I do is some serious analysis. And for doing serious analysis, the connection which Blender gives us is not enough. I mean, to get some, to do some serious analysis, we really need true intersection between these two one-dimensional manifolds. The case, and for that, we need to solve the so-called connecting problem. Connecting problem is a problem which you want to connect one-dimensional, some lower dimensional, some invariant manifolds by adding some small perturbation. And this problem is kind of difficult. And there's one result which is known in C1 topology. That's a result of Hayashi, which says that in C1 topology, you can do the connection by adding. It is a possibility of connecting, because here's the important observation is that the blending process of blenders only takes place inside blenders. I mean, what Blender tells you is that if you have some one-dimensional objects, then if you take the image of it, then it turns to be the two-dimensional object. That's a rough statement of what Blender tells us. But if you check the statement very carefully, so have this condition, then by the existence of Blender, you have the accumulation of these one-dimensional objects. But and you want to connect this one-dimensional object, and for that you do some perturbation outside the blender. And the perturbation outside the blender doesn't give any effect about the dynamics inside the blender. So you can get the connection almost for free. All right. So that's the information about one-dimensional manifolds. And the last condition I require is that the existence of partial hyperbolicity around this object, around the object which I have described now. So this is a summary of what I required. So we have two fixed points with different indices. We have 2 point intersections where the signatures are fine invariants and Shibarian derivatives are different. And I require the which connects these one-dimensional objects somewhere far away from these two fixed points. And one can check that these all conditions are CR open conditions. So if you look at the neighborhood of this map, you have this condition. What I proved is that if you look at the small neighborhood of this map, then CR generic map exhibits super exponential growth of number of periodic points. All right. Let me give you some ideas of the proof of this result. So there are a couple of steps, but it's not hard to understand. So the first step is that if you have initial map, then by adding some CR small perturbation, you can create one flat periodic points. Where one flat, or in general, K flat periodic points in this talk means that so what K flat periodic point is a periodic point first, and it's not hyperbolic because it has neutral eigenvalue in the center direction. And K flat means that if you can do the calculation of differentials first return map along the center direction, and K flat here means that the derivatives up to K vanish in center direction. So what I do first is that from the assumption, you can create one flat periodic point. And for this periodic point, I have some information about affine invariant Shibarian derivatives. That's the first step. And the second step is following. If you have, I think this statement sounds a little bit strange for you, but suppose you have 8 K-flat periodic points. Then by adding some small perturbation, you can create one K plus 1 flat periodic point. So that by adding some CR small perturbation, so that roughly means that by sacrificing 8 K flat periodic points, you can get some periodic point which has one more flatness in the center direction. So this is kind of induction step. So what I do by using step 1 and step 2 is the following. So we have original map. And from this original map, I create a lot of one flat periodic points. 8 part to R minus 1, where R is a regularity, and 8 R minus 1 flat periodic point. And from these periodic points, I create a lot of 2 flat periodic points, 8 part to R minus periodic points. Since, you know, by using 8 points, you can create 1 periodic point with 1 more flat number. It can be obtained just dividing by 8. You continue this construction, and finally you will arrive at 1 R flat periodic point. Then there's one general statement which says that for CR diffeomorphism, if you have R flat periodic point, then by adding some small CR small perturbation, arbitrary small perturbation, you can create an oscillation in the center direction, and as a result, you can increase the number of periodic points as much as you want. So I think now the proof is almost obvious. By using this, you can, so these 3 propositions says that by adding small perturbation, you can increase the number of periodic points as much as you want. So combining Bell's category theorem argument, you get the theorem. This is a pictorial explanation of what I did. So you know, originally we have this robust heterodimensional, and by adding, you get 1 flat periodic point. And by using this 1 flat periodic point, you sacrifice a lot of points, and you get a lot of 2 flat periodic points. And you continue this construction, and as a result, you get this 1 flat periodic point, and that's it. I have 5 minutes, and so now I would, all right. So let me say a couple of words about the proof of C infinity case. So yes, this is a nice slide. I mean, so the idea which I explained gives you the proof for CR case, but this is this argument almost automatically gives you C infinity case as well. Because recall that 2 C infinity maps are close in C infinity topology if they are CS close where S is really large. So to obtain C infinity result from this result, what you need to do is the following. First, you fix S very large. Then and I forgot to say that you know, in step 1 and step 2 and step 3, these are CR small perturbations, but the perturbations themselves are realized as composition of C infinity maps. So first you fix very large S, and fixing S, you do this construction, and finally you arrive at 1 C infinity map, which has S flat periodic point, and adding CS small perturbation, you get a lot of periodic point, and so that's it. So C infinity case is not a mysterious thing in this problem. And so, well, I would say a couple of words for the proof of proposition 1. In proposition 1, the main part of the proof is the following. Suppose that you have some heterodimensional cycle. So this point is connected, and this points are for this point you have a real connection. Then what I proved is that by adding some C infinity small perturbation, you can create 1 flat periodic point around these objects. But still, you have some information about affine invariants and Schwarzschild derivatives for this newly created neutral points. So that's a novelty here. And for the proof, what I did is that there's a profound, deep analysis done by Diaz and Rocha, which investigates the local bifurcation around heterodimensional cycles. So the creation of 1 flat periodic points around this structure is not a completely, classical topic. Here the novelty is that we can get some information about signature of affine invariants and Schwarzschild derivatives. That's something new. I should say this is something mysterious because recall that I didn't assume any bunching condition or pinching condition so far. And this is a kind of comparison result. I want to compare the information about second derivatives and third derivatives, but without any bunching condition. So this is something mysterious. But we can do that. Actually, by doing direct calculation, you can see that the center derivative in the center direction of this new one-flat periodic point and heteroclinic points are really, their distances are really large in C2 distance or C3 distance. You can calculate it by direct calculation. So for C2, so for second derivatives or third derivatives, it's very hard to believe that you can get some comparison results. But remember here, we are dealing with affine invariants or Schwarzschild derivatives, and you should recall, although I don't remember the exact formula. In their formulas, there are some divisions, there are some fractions. And because of the existence of these fractions, you cannot compare the C2 derivative of these maps in the center direction, but you can compare the affine invariants or Schwarzschild derivatives, and that's something new. And actually, well, the second step is much more complicated, but I think now the time is over. So, and actually, I'm feeling hungry now. So, if you have any questions, so your questions are totally welcome. So, I think now it's a good time to finish. Thank you very much for your attention. Question because I